Hit that like button and subscribe. Let us know where you're watching from and what time it is for you right now. The Quiet Architect of Power, Sir Harry Ricardo and the Science of Combustion. In 1915, a young British engineer constructed an engine of such remarkable efficiency that the War Office, in their skepticism, outright refused to accept the initial performance results. His newly developed prototype demonstrated several unprecedented advantages. It consumed a significantly smaller amount of fuel, delivered a greater power output, and operated at a noticeably cooler temperature than any engine currently in military service. The military officials were convinced there had to be a fundamental error in the recorded measurements. However, the engineer was Harry Ricardo, and the meticulously documented figures were entirely correct. Britain was deeply immersed in the conflict of the First World War, facing a critical, urgent need for dependable engines to successfully power their growing fleets of tanks, supply lorries, and military aircraft. The vast majority of these existing units were plagued by frequent overheating, consistent misfiring, and a ruinous waste of precious fuel supplies. Ricardo's test engine, which was modestly built in a small workshop located in Sussex, appeared to be an invention that defied all accepted mechanical convention of the era. His profound discovery that the true secret to enhanced power resided in precisely how fuel and air were mixed immediately prior to ignition was an insight that would eventually and irrevocably redefine the discipline of mechanical engineering. Yet at that specific time, only a few individuals outside of his dedicated small team truly grasped the magnitude of his achievement. Harry Ralph Ricardo was born in 1885 in London into a family environment that highly valued invention and scientific inquiry. He pursued his studies in mechanical sciences at Trinity College, Cambridge, where he rapidly developed an intense obsession with the internal combustion engine. While most of his fellow students were content merely to conduct simple, basic steam experiments, Ricardo dedicated countless nights to an intensive analysis of complex phenomena such as flame fronts, optimal compression ratios, and the mechanisms of heat losses. His primary objective was to thoroughly understand why engines wasted energy and, crucially, how this waste could be completely halted. Following his graduation in 1908, he immediately began the demanding work of designing experimental petrol engines specifically for use in motorbikes and motor cars, maintaining an unwavering focus on cylinder efficiency and achieving smooth, controlled combustion. His earliest prototypes were already capable of producing substantially more power than the majority of commercial designs then available. But Ricardo held little interest in the business of selling machines. What truly captivated his scientific mind was combustion itself, the largely invisible chemistry occurring within a robust metal cylinder that successfully managed to convert a liquid vapor into kinetic motion. When the war commenced in 1914, Britain's newest and most potent military asset, the tank, was instantly facing serious mechanical issues. The very earliest prototype tanks were equipped with heavy, notoriously unreliable engines that had been repurposed and borrowed from standard farm tractors. These machines suffered from continuous overheating, were prone to stalling disastrously in the thick mud, and on occasion would even catch fire after only a few short hours of operation. The Army, in desperation, reached out to Ricardo's fledgling company, Ricardo Engineering, for urgent assistance. He accepted the challenge, relocated his operations to Shoreham by sea, and immediately commenced what would undoubtedly become one of the most influential engineering studies of the entire war. Within a period of mere months, Ricardo's modest workshop had successfully constructed an entirely new, high-performance power unit. By applying careful, detailed analysis of heat transfer dynamics, vastly improving the air-fuel mixture process, and implementing a fundamentally redesigned cooling system, his new engine possessed the remarkable capability to run for hours under heavy load without succumbing to overheating. When this engine was subsequently tested on the Mark V tank, its performance was nothing short of flawless. Soldiers who had endured months of wrestling with dangerously temperamental machines were now commanding vehicles that could finally maintain continuous movement even under heavy enemy fire. The War Office, having been initially highly skeptical, suddenly and profoundly realized the full extent of Ricardo's achievement. His design did not simply offer a modest improvement in performance. It transformed the tank from a serious mechanical liability into a dependable, highly effective weapon. For the very first time, armored personnel could operate with a new degree of confidence across the treacherous terrain of the Western Front. If you've made it this far, you are exactly the dedicated and curious audience we make these videos for. Thank you for your support. Unlike many inventors of his time, Ricardo was not guided by mere intuition or simple luck. His trust was placed entirely in data. He went on to build some of Britain's first truly scientific engine test stands, utilizing them to meticulously record crucial variables such as pressure waves, operating temperatures, and flame speeds with incredible, scrupulous precision. His personal notebooks were extensively filled with complex calculations linking fuel chemistry directly to engine geometry, advanced mathematics that the vast majority of factories of that era never even considered. Colleagues often remarked that he approached every single engine as if it were a laboratory experiment, rather than simply a commercial product. This rigorous scientific discipline granted him a unique and deep insight into a chronic problem that plagued virtually every internal combustion engine produced in the early 20th century: detonation, commonly known as knocking. When fuel ignited prematurely, it resulted in a catastrophic loss of power and had the very real potential to destroy an engine in a matter of seconds. Ricardo initiated a detailed study of how compression and fuel quality interacted, thereby establishing the fundamental groundwork for what is now universally known as the octane rating. His groundbreaking research conclusively proved that by precisely controlling the rate at which fuel burned, engineers could safely extract significantly more power from an engine of the exact same size.
By the time the war concluded, Ricardo's name had begun to quietly spread throughout the global engineering world. His expertly redesigned tank engine became the standardized pattern used for all subsequent British armored vehicles. More importantly, his highly sophisticated understanding of combustion efficiency began to profoundly influence aircraft manufacturers and automobile companies alike. Iconic firms such as Rolls-Royce, Vauxhall, and Bentley all actively sought his expert advice throughout the 1920s. He deliberately avoided chasing large contracts or public notoriety. Instead, he maintained his focus on relentlessly refining his scientific methodologies, publishing technical papers that were considered to be more akin to physics treatises than simple mechanical manuals. Every single paragraph he authored replaced outdated superstitions with measurable cause and effect. In a field that had historically been overwhelmingly dominated by crude trial and error, Ricardo successfully introduced order and the precision of mathematics. In 1919, he formally incorporated his business as Ricardo Company Limited and promptly constructed a dedicated state-of-the-art research facility at Shoreham. There, he continued his vital work, exploring in depth how various fuels behaved when subjected to intense pressure and heat. Every single test result, every design diagram, and every instance of engine misfire was carefully logged and exhaustively studied. His laboratory quickly became a quiet powerhouse of British innovation, generating crucial data that would soon guide and inform engine design across the entire planet. What had originally started as an urgent tactical wartime solution was rapidly evolving into a lifetime-long pursuit of pure discovery. The complex problems surrounding knocking, efficiency, and power output were clearly not merely concerns of the military. They represented the very future of global transport itself. Ricardo intuitively understood that as engines became increasingly faster and smaller, precision in combustion would be the sole factor determining all future progress. He had successfully transformed the fundamental act of burning fuel into a rigorous science. And soon, this pioneering science would ensure that Britain's engines, on land, at sea, and in the air, would become stronger and more capable than they had ever been before. After the conclusion of the First World War, Harry Ricardo's reputation as one of Britain's most foremost and authoritative combustion specialists was firmly and irrevocably established. The Army had witnessed firsthand the immense capabilities of his tank engines, and industry was finally beginning to grasp that the same rigorous scientific approach could fundamentally transform civilian power as well. His once small workshop at Shoreham was now a fully equipped advanced research laboratory, a professional environment where engines were no longer constructed based on simple instinct, but rather by the unerring precision of mathematics. The war had successfully instilled one paramount lesson in Ricardo, that reliability was infinitely more important than mere raw power. The temperamental tanks of 1916 had proved beyond a shadow of a doubt that an engine capable of working flawlessly in a controlled laboratory environment was utterly useless if it failed critically in the midst of a battle. Consequently, in the years that followed, he wholly dedicated himself to a complete understanding of combustion behavior under every conceivable operating condition: extreme heat, immense pressure, high altitude, and varying fuel quality. His methods, though sometimes described as obsessive, were profoundly revolutionary. Where other engineers relied on simple guesswork, Ricardo relied on precise measurement. He began his new line of inquiry by meticulously dissecting the underlying causes of detonation. The sudden, destructive knock that frequently destroyed pistons was not a random occurrence, as most then believed. It was, in fact, the direct result of unstable fuel igniting unevenly before the intended spark. Ricardo ingeniously designed transparent cylinders and employed advanced optical instruments to observe the flame itself in real time. He discovered that the precise shape of the combustion chamber, the turbulence level of the air-fuel mixture, and the chemical volatility of the petrol all worked together to determine how smoothly an engine would run. This was the type of detailed, complex work that no commercial car manufacturer possessed the necessary patience or precision to carry out, but Ricardo took it upon himself. By the early 1920s, major British corporations were routinely sending him engines for rigorous testing. Rolls-Royce sought his expertise for their early aero engine projects, while Vauxhall and Crossley extensively consulted him for improving their commercial vehicles. His groundbreaking research on octane numbers, which is a universally accepted measure of a fuel's inherent resistance to detonation, rapidly became a definitive benchmark for the entire petrol industry. This finding established that the higher the octane rating, the more compression an engine could safely withstand, and consequently, the more power it could successfully generate. This simple yet profound relationship changed the course of engine design for the rest of the century. Simultaneously, he began an important investigation into diesel engines. They were then still viewed as crude, noisy machines, but he immediately recognized their vast potential for thermal efficiency. He focused on developing combustion chamber shapes that forced diesel to burn much more evenly, which dramatically reduced smoke output and increased power. These pivotal experiments laid the critical foundation for the modern high-speed diesel engine, the technology that would soon come to dominate commercial transport worldwide. By the mid-1920s, his company, Ricardo and Company Engineers, had successfully grown into one of the most respected independent research organizations in all of Britain. Governments, major car makers, and even aircraft manufacturers routinely sent their most sensitive designs to Shoreham for rigorous testing. Every single experiment was meticulously logged, and every observed anomaly was exhaustively explained. Ricardo firmly believed that successful engineering was as much about understanding failure as it was about achieving success. If a piston cracked or a valve burned out, he would personally study it under a microscope until he knew the exact, precise reason why.
The interwar years also saw him serve as a key advisor to the Air Ministry, where his unparalleled knowledge of fuel behavior proved absolutely vital. Aircraft engines of the period often suffered badly from detonation at high altitudes, where the surrounding air was thinner and effective cooling was less available. Ricardo's comprehensive studies ultimately led to the rapid development of special high-octane fuels and greatly improved combustion chamber designs, allowing the nation's pilots to climb much higher and fly significantly faster without risking the destruction of their engines. This quiet, persistent work, conducted in laboratories and military hangars, would later prove to be decisive when Britain faced its moment of greatest national peril. Although he was by now one of the most highly respected engineers in the country, Ricardo purposefully avoided the public spotlight. He had a strong dislike for self-promotion and much preferred the focused company of his instruments and his apprentices to attending lavish banquets or accepting grand awards. His laboratory remained modest, yet highly disciplined, every tool neatly in its correct place, every test meticulously documented. Visitors often remarked on the calm, focused atmosphere within the building, as if the usual noise of industry had been completely replaced by the precision and quietude of science. By the 1930s, Ricardo's published findings were actively shaping not only new military designs, but also the broader civil progress. His detailed papers on heat efficiency, fuel injection, and air turbulence were widely circulated throughout Europe and America. He collaborated closely with Shell and BP to develop better, more effective refining techniques, thereby ensuring that Britain's petrol supply was cleaner and chemically more stable. When the Royal Navy began the extensive process of fitting diesel engines into their submarines, it was Ricardo's critical combustion research that made them reliably operational. He had now advanced far beyond the role of a mere engineer. He had become a teacher of fundamental scientific principles. His core philosophy was elegantly simple. Every improvement begins with rigorous measurement. Guesswork, he often stated, is the enemy of progress. That unwavering conviction echoed through every single project that bore his name. As the ominous clouds of war began to gather once again over Europe, Ricardo's important work took on a renewed sense of urgency and necessity. The engines destined for the coming conflict would need to be demonstrably faster, tougher, and significantly more efficient than any before. The laboratories at Shoreham now buzzed day and night with relentless experiments, testing new fuels, new piston materials, and new cooling methodologies. Ricardo's team, though remaining small in size, consistently produced results that profoundly influenced aircraft and tank production across the entire nation. He did not view himself as being part of the war machine itself, but rather as an indispensable part of the nation's survival mechanism. He frequently made the point that good engineering saves lives, because reliability prevents catastrophic failure. In 1939, when Britain once again found itself engulfed in war, his ideas, quietly developed over many preceding decades, became the very difference between victory and defeat.
By that time, the Ministry of Aircraft Production and the Royal Air Force were critically reliant on Ricardo's essential research regarding combustion control and high-octane fuel. Every single Spitfire and Hurricane that soared into the skies did so with engines that had been meticulously fine-tuned by the very principles he had discovered years earlier in his quiet Sussex lab. Harry Ricardo's war was never fought in muddy trenches or dangerous cockpits, but rather in test cells filled with smoke, pressure gauges, and endless sheets of precise data. And it was a war for which he was uniquely and perfectly prepared to win. When the Second World War erupted in 1939, Harry Ricardo was 54 years old, still professionally active, perpetually curious, and still routinely working late into the night at his Shoreham laboratory. His research conducted during the interwar period had already successfully shaped Britain's core engine technology. But now, his profound knowledge would play a defining role in the survival of a nation. Britain's entire air defense system, military mobility, and logistical capabilities were all critically dependent on both fuel efficiency and engine reliability, two specialized fields in which Ricardo had rightfully become the unquestioned, quiet authority. At the very outbreak of the war, the Ministry of Aircraft Production and the Royal Air Force immediately turned to him once more. Aircraft engines were being pushed well beyond their safe design limits, particularly during high-altitude air combat. When these engines detonated, they suffered catastrophic power loss or failed completely, frequently costing the pilots their lives. Ricardo's previous, extensive work on detonation, compression ratios, and fuel quality had already proved conclusively that the most effective answer lay not in simply achieving more power, but in implementing better combustion control. His research consequently became the fundamental backbone of Britain's high-octane fuel strategy. Collaborating closely with Shell and the Air Ministry, Ricardo's dedicated team successfully perfected new fuel blends that safely allowed for significantly higher compression without the destructive knocking. This pivotal advance meant that major fighter engines, such as the legendary Rolls-Royce Merlin used in the Spitfire and Hurricane, could produce more power without any associated damage. Those crucial extra revolutions per minute, achieved through the intelligent application of chemistry and engineering precision, granted Britain's pilots the vital, decisive edge in the skies during the pivotal Battle of Britain. That victory was indisputably as much a triumph of advanced engineering as it was of human courage.
Ricardo's name was seldom, if ever, mentioned in wartime newspapers, yet his scientific fingerprints were indelibly marked on nearly every British engine. His firm actively worked on power units for tanks and armored vehicles, marine diesel units for the Royal Navy, and essential auxiliary generators for field operations. Every single design benefited directly from his methodical, unwavering approach: measure, test, refine. His laboratory quickly became recognized as a critical national asset, guarded and officially operated under direct government supervision, but always under his personal, quiet leadership. He frequently asserted that good engineering wins wars before they even begin. For him, this philosophy translated into foresight, effectively solving complex mechanical problems in the workshop long before they could possibly manifest in the chaos of battle. While the primary focus of other aircraft engineers was on speed and raw firepower, Ricardo instead focused intensely on endurance, how to make sophisticated machines run longer, smoother, and while consuming fewer valuable resources. The results of his vital fuel research extended well beyond the immediate combat needs. The exact same principles he developed dramatically improved the performance of military lorries, ambulances, and even the portable generators used by medics in the field. Despite the intense pressure and secrecy surrounding wartime operations, Ricardo continued to publish technical papers, carefully wording them to obscure sensitive details while still effectively advancing the wider field of science.
His profound studies on heat loss, air turbulence, and the pressure propagation inside cylinders quickly became foundational, essential material for the next generation of engineers. Universities and major companies across the globe relied heavily on his detailed data, even if they remained unaware of its profound military importance. One of his most crucial wartime accomplishments was the expert refinement of diesel engines for naval service. Submarines and vital escort ships demanded engines that could operate for long durations under highly variable loads without suffering overheating. Ricardo's expertise in advanced airflow and cooling systems made those engines far more efficient and critically reliable. These improvements were hardly glamorous, but they unequivocally saved countless lives at sea. In the concluding years of the war, Ricardo began experimenting with gas turbines, a cutting-edge idea that connected directly back to the very combustion principles he had dedicated decades to studying. He astutely recognized in them the enormous potential for the next great leap in power generation. Though his own company's primary focus remained on piston engines, he maintained close consultative contact with the dedicated teams developing the world's first jet engines. He deeply admired their ambitious goals, but he also offered a crucial warning that efficiency, not sheer speed, would be the defining factor of the future. As the arrival of victory drew near in 1945, Ricardo's laboratory remained a hive of relentless work rather than public celebration. His engineers were already actively analyzing the complex requirements of the post-war world: civilian transport, the urgent rebuilding of industry, and the essential conversion of military research into peaceful, productive applications. He firmly believed that the hard-won lessons of war should directly lead to superior technology for ordinary life: quieter, more durable engines, cleaner fuels, and machines that fundamentally wasted nothing. By the war's end, Britain's engine technology was globally recognized as being among the most advanced in the entire world. A considerable amount of that progress could be traced directly back to Ricardo's unwavering insistence that every problem had a definitive, measurable solution. The octane system he had pioneered decades prior was now the globally accepted international standard. His innovative cooling designs were being extensively copied across Europe and America, and his breakthrough theories concerning turbulence and combustion dynamics would soon profoundly influence both rocket and jet propulsion. When peace finally returned in 1945, Ricardo was rightly recognized as one of the silent architects of Britain's wartime engineering strength. Yet he initially declined formal honors, preferring instead to immediately return to his research. He often philosophized that invention never truly belonged to the original inventor. Once scientifically proven, he believed, it belonged entirely to the world. What truly mattered to him was not personal fame, but fundamental function. Harry Ricardo's war had been effectively fought in silence, employing equations instead of gunfire, and precise measurements instead of medals. But when Britain's engines roared into action, it was his science that ensured they roared longer, louder, and smarter than anyone else's.
Throughout the 1950s and 1960s, the engineering world around him underwent a dramatic transformation, shifting from basic pistons to sophisticated turbines, and from complex mechanical linkages to advanced electronic control. Yet Ricardo's core principles of measurement and analysis steadfastly endured. His seminal book, The High-Speed Internal Combustion Engine, remained the unchallenged standard reference text for engineers everywhere. This was not merely because it provided formulas, but because it fundamentally taught how to properly think, observe, test, quantify, and refine. He strongly encouraged active collaboration between universities and major industry, deeply believing that research held little value if it remained permanently behind closed doors.
Long before environmentalism became a widely recognized concern, he issued a clear warning that the engineer's duty was to make machines cleaner and demonstrably more efficient, asserting that waste in any form was a critical enemy of civilization itself. Even well into his 80s, Ricardo still dedicated time at the test benches, quietly analyzing pressure traces and carefully noting temperature drops with the exact same boundless curiosity he had exhibited as a young student at Cambridge. Visitors often found it genuinely difficult to discern where his retirement had officially begun, because for him, scientific inquiry was simply a fundamental way of living. Sir Harry Ricardo passed away in 1974, at the age of 89. He left behind no physical monuments, only the evidence of motion. More efficient engines, authoritative textbooks, and a profound philosophy of scientific precision that has indelibly shaped the modern world. His life's work successfully bridged the vast ages of steam, petrol, and jet propulsion, conclusively proving that genuine progress is not dependent on mere chance, but rather on accurate measurement. He once thoughtfully wrote, "The engineer's task is not to invent energy, but to prevent its waste." That simple, profound idea still drives every efficient engine built today, a quiet, powerful echo of the man who successfully turned combustion into a true science and gave the 20th century its fundamental rhythm of power. If you enjoyed this deep dive into engineering history, share this video with a friend who loves science.